Hello students, in our previous class we learned about colloids, their classification and different methods employed for the purification of colloids. Today we are going to deal with some of the important and interesting properties of colloids. The properties of colloids are classified into kinetic property, which deals with Brownian movement, optical property that deal with Tyndall effect, and electrical property that deal with the formation of a double layer, and two other important phenomena like electrophoresis and electroosmosis, which are actually the consequence of the formation of the electrical double layer. Also, we will discuss about the coagulation of colloids and some of its application in industry. First of all, kinetic property. Students, can you imagine that it was actually a Scottish botanist, Robert Brown, who first discovered the kinetic property of the colloid? Yes, in 1827, Robert Brown, while looking through a microscope at the pollen of the plant Clarkia pulchella immersed in water, visualized a ceaseless zigzag motion. When the pollen of the plant immersed in water, it actually formed a colloid, and it was the motion of these colloidal particles that he observed. This movement of the colloidal particle is known as Brownian movement. It was Albert Einstein who gave a scientific explanation to Brownian movement. Thus, the ceaseless erratic zigzag motion exhibited by colloidal particle is called Brownian motion or Brownian movement. The reason behind this motion is the unequal bombardment of the colloidal particles by the constantly moving molecules of the dispersion medium. During such bombardment, the molecules of the medium impart momentum to the colloidal particle, get knocked here and there. Next is the optical property. In 1869, a famous Irish physicist, John Tyndall, while carrying out observations of solutions and colloids, noted that a beam of light passing through a colloidal suspension is visible, but cannot be seen when it passes through a solution or a pure substance. As deduced by Tyndall, this phenomenon is due to the fact that in a colloidal suspension, light is scattered by the many small particles it contains, but which are absent in homogeneous mixture and pure substances. Moreover, the Tyndall effect results in the visualization of a blue or violet color when the particles present are very small, but will cause the color red to appear when the particles are larger in size. Thus, this scattering of light by the colloidal particles is known as Tyndall effect, and the illuminated path is known as Tyndall beam or Tyndall cone. Students, have you noticed the visibility of the path of light coming from the projector in a cinema hall? It is actually due to this Tyndall effect. Here, the light is scattered by the dust and other particles of the colloidal size present in the air. Intense Tyndall effect is observed only when the diameter of the dispersed particle is not much smaller than the wavelength of the light used, and there is a large difference in the refractive indices of the dispersed phase and dispersion medium. Here, the second condition is related to the characteristics of the soul under consideration. This condition is fulfilled by most lyophobic souls, and as a result, lyophobic souls generally show a strong Tyndall effect. However, for most lyophilic souls, the difference in refractive indices of the dispersed phase and dispersion medium is usually small due to the presence of a heavy sheath of solvent around the soul particles. As a result, lyophilic souls usually show only a very weak Tyndall effect. Tyndall effect and Brownian movement can be used to determine the particle size of souls. Now, we will discuss about the electrical properties of colloids. Colloidal particles carry an electric charge, either positive or negative. All the particles of a particular colloidal dispersion carry the same charge. In most cases, the charge on colloidal particle originates due to the preferential adsorption of ions from the solution by the particles. In aqueous sols of colloidal electrolytes, self-dissociation and formation of ionic micelles causes the presence of charged sol particles. Example, in aqueous dispersion of soap, the anions RCOO- ions aggregate together to form negatively charged ionic micelles of colloidal size. Sol particles may become charged due to various other reasons also, such as electron capture during electrode dispersion or frictional electrification through rubbing with the molecules of the dispersion media, etc. Now, what is an electrical double layer? According to Helmholtz, the electrical double layer of positive and negative charges is generally formed at the surface of separation between the two phases. The stability and electrical properties of colloidal dispersion can be readily explained on the basis of the existence of such an electrical double layer in the interface between the dispersed phase and dispersion medium. The electrical double layer present at the liquid-solid interface in a sol consists of a fixed layer and a diffuse layer or mobile layer of equal and opposite charges, and these are formed from the positive and negative ions present in the system. In a position of close proximity to the fixed layer of charges, there will be more ions of opposite sign present in the diffuse layer due to preferential attraction. This charge separation gives rise to a potential that falls gradually across the diffuse layer into the bulk of the liquid, where the charge distribution is uniform and the liquid is electroneutral. The fixed layer consists of a layer of either positive ions or negative ions held firmly on the solid. The ions selectively adsorbed by the sol particle constitute this fixed layer. The diffuse layer consists of a mobile layer of ions extending some extent to the liquid phase. It contains both positive and negative ions, and their statistical distribution is such that the net charge is exactly equal but opposite to that of the fixed layer. This means that one kind of ions, either positive or negative, called counter ions, would be found in excess in the diffuse layer to neutralize the charge on the fixed layer. The electrical potential at the position of closest approach of ions to the surface fixed layer with reference to the bulk liquid is called the electrokinetic potential or zeta potential. If the electrical double layer at a solid liquid interface is regarded as a condenser with parallel plates d cm apart, each carrying a charge E per centimeter square, it has been derived from the electrostatics that the zeta potential is given by zeta equal to 4 pi ED by capital D, where capital D is the dielectric constant of the liquid. Next, I am moving on to the consequences of electrical double layer. Two electrokinetic phenomena observed as a result of the electrical double layer are electrophoresis and electroosmosis. First one is electrophoresis. When a colloidal solution is placed in an electric field, the electrically charged colloidal particles migrate towards the oppositely charged electrode. This phenomenon is called electrophoresis. Electrophoresis can be studied by taking colloidal solution in a U-tube in which the two platinum electrodes are dipped. On applying a potential difference across the electrode, it is observed that the colloidal particles move to the oppositely charged electrode. Once the charged particles reaches the electrode, it gets neutralized and settle down. Electrophoresis may be explained on the basis of electrical double layer postulated as present in the interface between solid and liquid phases. When an EMF is applied, the oppositely charged fixed and diffuse layer are displaced with respect to each other. since the charged soul particles are now free to move and they migrate towards the oppositely charged electrode. In the case of certain lyophilic colloids having amphoteric character, example proteins, the soul particle will carry positive charge below a certain characteristic pH and negative charge above that pH. The soul particle would carry no net charge and hence will not show electrophoretic motion. This pH is known as isoelectric point. The isoelectric point of albumin is 4.9 and that of gelatin is 4.8. Now we can move to electroosmosis or electroendoosmosis. If the electrophoretic motion of the dispersed particles of a soul is prevented by suitable means, the dispersion medium begins to move in an electric field. This phenomenon is known as electroosmosis. Electroosmosis may be explained on the basis of the electrical double layer postulated as present at the solid-liquid interface of a soul. When an EMF is applied, the oppositely charged fixed and diffuse layer are displaced with respect to each other. Here, since the charged soul particles are not free to move, the diffuse layer in the liquid phase move together with the liquid towards the oppositely charged electrode. The sign on the charge of the diffuse layer determines the direction of electroosmotic flow. The image shows an apparatus suitable for studying electroosmosis. The soul in the middle compartment A is kept separated from water in the side compartments C1 and C2 by means of two dialysing membranes D1 and D2. When electric field is applied, water begins to move. If the soul particle carry positive charge, water will carry negative charge. So, it will move towards the positive electrode kept in C1, causing the level of water in the side tube S1 to rise. On the other hand, if the soul particles are negatively charged, water will carry positive charge. It will then move towards the negatively charged electrode kept in C2, causing the level of water side tube S2 to rise. There are mainly two reasons for the stability of souls. Since the colloidal particles carry similar charges, there will be repulsion between like charges. It can account for the stability of souls. Brownian motion is also responsible to some extent for the stability of colloids as it counteracts the force of gravity acting on the colloidal particles. The precipitation of the dispersed phase of a colloidal solution through the induced aggregation of the particles is known as coagulation or flocculation. Different methods are employed for coagulation. First one is the persistent electrophoresis. Here, the soul is subjected to the action of electric field and the particles of the soul will migrate to the oppositely charged electrode. If this electrophoresis is permitted to proceed, the soul particle will reach the oppositely charged electrode will aggregate, which results in the coagulation of the soul. For example, in an electric field, the negatively charged arsenic trisulfide soul get coagulated around the positive electrode, while the positively charged ferric hydroxide soul get coagulated around the negative electrode. Second method is the persistent dialysis. When a soul is subjected to prolonged dialysis, the traces of electrolyte present in it is removed. This destabilizes the soul since the particles lose their charge in the process and the soul gets coagulated. For example, when a positively charged ferric hydroxide soul is subjected to prolonged dialysis, the Fe3+ ions adsorbed onto the particles are lost. This causes precipitation of ferric hydroxide. Next method includes the addition of an oppositely charged soul. Here, the mutual neutralization of the two kinds of oppositely charged particles occurs and thus the dispersed phase of both souls get precipitated. Example, is the addition of suitable quantity of negatively charged arsenic trisulfide salt into positively charged ferric hydroxide causes mutual neutralization of both. In the fourth method, addition of electrolyte will lead to coagulation. Here, the colloidal particles takes up oppositely charged ion from the electrolyte and get their own charges neutralized. The neutral particles then aggregates. Example, negatively charged arsenic trisulfide salt is coagulated by adding some barium chloride solution. Here, the Ba2+ is the active ion which causes coagulation. Next is Hardy-Schurz rule. It states that the greater the valency of the ion bearing a charge opposite to that on the salt particles, greater is its power to cause coagulation. For example, the power of Na+, Ba2+, Al3+ to cause coagulation of a negatively charged salt would be in the order Al3+ greater than Ba2+ greater than Na+. Similarly, in coagulating a positively charged salt, the order of the power of some active ions is given as FeCN6 4- greater than PO4 3- greater than SO4 2- greater than Cl-. Next is flocculation value. The minimum concentration of an electrolyte required to cause coagulation or flocculation of a salt is called its flocculation value. It is usually expressed in millimoles of the electrolyte per liter of the salt. Example, the flocculation values of sodium chloride, barium chloride and aluminum chloride for the negatively charged arsenic trisulfide salt are respectively 52, 0.69 and 0.093. Similarly, the flocculation values of KCl, K2SO4 and K3FeCN6 for the positively charged ferric hydroxide salt are 102, 0.210 and 0.093 respectively. Now, we will discuss some of the industrial applications of coagulation. First one is in the production of rubber. Rubber latex is a colloidal solution of negatively charged rubber particles dispersed in water. Coagulation of latex using a coagulating agent like formic acid or acetic acid yields rubber. Next is the industrial smoke precipitation. Smoke is a colloidal solution of electrically charged carbon particles in air. The smoke let out into air is precipitated and removed by making use of the electrophoretic motion of its particles and subsequent coagulation in Cottrell smoke precipitator. Another important application is in sewage disposal. Sewage water contains particles of dirt, dust, mud and garbage of colloidal size. As these particles remain dispersed in water, forming a colloidal solution and carry charges. The sewage is passed into a large tanks fitted with metallic electrodes kept at high potential. Thus, as a result of electrophoresis, the colloidal particles get coagulated and settles down. This sewage sludge is often used as manure and remaining water is utilized for irrigation. Now, I would like to conclude by pointing out a consequence of coagulation observed in nature, that is a delta formation. River water is a colloidal dispersion of charged clay particles. When river water comes into contact with sea water, which contains several dissolved electrolytes, the colloidal particles of clay present in river water get coagulated by the action of these electrolytes. The precipitated clay get deposited to form delta. I hope the concepts we have discussed today is clear for you all. Thank you.